So the only thing we have left is the final. Would you gentlemen shut your bloody pie holes? Your blood pudding holes. So our final, you can take it Monday. Yep. So Monday is 12/11, 6 p.m. S1326, or Thursday 12/14, 2 p.m. 13/28. Okay, everybody's going to need to shut the hell up so I can, because we're going to have to talk about an entire topic today, so that you're ready for Physics 2. And those of you who are not taking Physics 2 need to learn this topic because it's going to be on the test. Okay. So, anybody have any questions about the final? And I know I owe you a lot of stuff, graded stuff. Oh, I have a test of yours. Yeah, now everybody's exam 3 is posted. Where did you take it? In the testing center? Okay, I remember that. Okay, I'll fix that. Everybody else. And yes. Yeah, same length of test. I might make it slightly simpler problems so I can fit 5 or 6 problems into the same amount of time. But that's, yeah, I'll write it to be an hour test. Everybody will be done within an hour and a half, roughly, you know. Okay, so anybody have any questions about conservation of energy? That's good. Okay, no particularly. We miss you, Josh. Yeah. Okay, so now we're going to talk about rotational kinetics. Yes. You should write down rotational kinetics. And before we can do that, so remember when we talked about particle kinetics, we had first spent a lot of time talking about particle kinematics, position, velocity, acceleration. And then we did kinetics and talked about how to use the kinematic stuff with force and mass. So first I have to introduce these two angular kinematic quantities, and rotational and angular mean the same thing. Oh, let me say a little bit about that actually. So angular and rotational kinetics are very naturally, angular kinetics, rotational kinetics, and circular motion are very naturally, go together really naturally. A lot of the things that you do with rotational problems involve circular motion. And so I just want to be clear about the difference between those two things. So circular motion, like right now I'm in circular motion, if you look at any one point on my body from the top down view, it's moving in a circle, But now what we're talking about is we're getting away from particles. We're talking about objects that can have orientation, so real objects. And so rotational motion, angular motion, is when the orientation of the thing is changing. So now, it could also be moving in a circle, but now it's doing this. Okay. So that's what we're talking about now, the change in orientation. And before we can get into the kinetic stuff, we have to first define angular velocity. And angular acceleration. And one thing that's going to be very helpful in this whole discussion of angular kinetics is that everything we talk about as an angular quantity has some analogous particle quantity. So angular velocity, we're going to see tons of similarities between that and particle velocity. And angular acceleration, there'll be tons of similarities with particle acceleration. And that's going to happen with every quantity we talk about. So it's going to make it a lot easier to remember how this stuff goes together. Okay, so first, angular velocity. So angular velocity is a directional quantity that tells how quickly an object's orientation is changing. The magnitude of the angular velocity is the angular speed which measures the angle an object rotates through per unit time. And then the direction, I guess I have an example of this. So RPM is an example of angular speed. Rotations per minute, you go through to do a full rotation, you go through a full 360 degrees. So if something's going, 1,000 RPM, it's going 1,000 times 360 degrees. So 360,000 degrees per minute. Okay, and that's angular speed. We are going to, instead of using degrees to measure angles, we're going to use radians now. You don't have to change your calculators because we're not going to use sine and cosine, so it won't matter whether you're in degrees or radians for that. Okay, let's say that a boat engine goes through 10,000 rotations per minute. I don't know if that's possible or not. Okay, so 10,000 RPM. The R is for rotations. The M is per minute. What's the angular speed in radians per second? Well, every rotation is 2 pi radians, a full time around. So we have, I'm going to write it as 10,000 rotations per minute. One rotation is 2 pi radians. And 1 minute is 60 seconds. And so we get 20,000 times pi divided by 60 radians per second. And that is about 1,000, right? A little over 1,000. Can someone divide that? .047, I'll just leave it like that, radians per second. Okay, so that's the magnitude of angular velocity. And, the easiest thing to relate this to is if you think back to one-dimensional motion. Remember that directional quantities, the direction was given by the sign, the plus-minus sign. And so, like if you had something moving in the negative direction with a speed of 20 meters per second, then the velocity would just be negative 20 meters per second. And it works the same here. So the sign of the angular velocity gives the direction. A positive sign means that the thing is rotating counterclockwise. You might think it makes more sense to make positive clockwise, but we don't get to choose. And negative means clockwise. Okay, so for example, a top is spinning clockwise with a constant angular speed of 10 rotations each second. What's the angular velocity? Well, first, let's just write the angular speed in terms of radians per second. So we have 10 rotations per second. And one rotation is 2 pi radians. And so we get 20 pi, that's 62.8 62.83 radians per second. And then we have to take the direction of the spin into account. Clockwise means it's negative. So the angular velocity is negative 62.83 radians per second. And we're always going to denote the angular velocity with the Greek letter omega, lowercase omega. So it looks sort of like a round W. Okay, so both of the two examples that we did so far were sort of thinking of the angular velocity being constant, but obviously like the rate of rotation could change, start out slow and speed up and slow down. And so how quickly the angular velocity is changing is measured by the angular acceleration, just like the particle, how quickly the particle velocity is changing is measured by the acceleration. So angular acceleration measures how quickly the angular velocity is changing. And just based on what you know about the relationship between velocity and acceleration from translational stuff, if something has a constant angular velocity, what do you think that means the angular acceleration is? Yep. That means zero angular acceleration. And you can think of those two things as synonymous. If one of these is true, the other one has to be true. And we are going to represent the angular acceleration as the Greek letter alpha, like the fish on the back of cars. Okay, so the definition of the angular acceleration relates to the angular velocity just exactly the same way it did for translational stuff. So, we've never used this equation, but I gave it when I was first defining acceleration. So can anybody come up with this formula? Angular acceleration is equal to, let's say the limit is time 2 minus time 1 goes to 0 of, do you remember anybody come up with that definition? So we did this, if you look back like early on in the class when we first talked about acceleration, this was the velocity at instant 2 minus the velocity at instant 1 divided by t2 minus t1. And it works just the same, except now these are the angular velocities. So angular velocity at instant 2 minus angular velocity at instant 1 divided by t2 minus t1. And because this relationship works exactly the same way, a lot of our interpretation stuff works out exactly the same. Like the first one is, like I said, if you have constant angular velocity, you have zero angular acceleration and vice versa. The other thing is, if so keep in mind, notice that if the angular velocity and the angular acceleration have the same signs, what do you think we know about the motion? So the rotations are speeding up. Exactly. And if omega and alpha have opposite signs, then the rotations are slowing down. The units for angular acceleration, well, actually, I didn't do it for angular velocity yet, so let me do it for both of them. Let's say the SI units for angular velocity are radians per second, and the SI units for angular acceleration are radians per second squared. Okay, any questions yet about that? Okay, so I've been talking about this close relationship between all of these variables that we have, all these angular quantities, and the old translational quantities that we're used to. So I want to write out a table of just all these angular quantities and connect them to the translational quantities that they're similar to. So let's say on this side we'll have particle, and on this side we'll have angular. So first of all, velocity vector is related to angular velocity. And the acceleration vector is related to the angular acceleration. Also, the definition of the translational acceleration is the limit as blah, 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 as this interval of time gets smaller of velocity vector at instant 2 minus velocity vector at instant 1 divided by t2 minus t1. And you have that same relationship for alpha. Okay, and then so, well, this is interesting. We have a relationship that says velocity final is equal to velocity initial plus a t final. That holds for angular stuff too. So angular velocity final is equal to angular velocity initial plus alpha t final. We're not going to use those. We won't do any problems like that, but that stuff holds. And then going to the we did the kinematic quantities. Now going to the kinetic quantities. What are the two new quantities we had to define when we went from kinematics to kinetics with particles? Before, so, well, if like any part of any kind of velocity, any kind of acceleration, any kind of position, that's all kinematics. So what were the two new things that came up when we went to kinetics? Force and one other thing. Mass. So so for particles, we have mass, and that tells you how resistant an object is to being accelerated. For angular stuff, we have this thing called, so it's going to be represented by capital I sub A. and it's called the mass moment of inertia about axis A. And just like the mass tells you how resistant an object is to being accelerated, this mass moment of inertia, we're just going to call it moment of inertia for short, tells you how resistant an object is to being rotated around that axis A. So if you think of something, so we're not talking about like friction or something being stuck that keeps something from rotating, but if you think of something rotating on like a surface, ice surface or something frictionless, different objects have different levels of difficulty to get them rotating, and what that depends on is that mass moment of inertia, and I'll talk about that more in a second. And then we had the force vector for particles, and we have something equivalent to the force vector here. I'm going to call it capital M sub A, and that's the moment or torque. Those are synonyms. Torque, yep, about axis A. And so just like a force tells you, how much acceleration you're going to get for a given object, the moment you apply to something or the torque you apply to something tells you how much angular acceleration you're going to get for some object. If you put a big torque on something, you'll get a big angular acceleration. Small torque will get a small angular acceleration. And then this is going to blow your minds. Okay. We do not say that here. Okay, so where kinetics went, particles was F equals ma. The big equation that we're heading to here is moment about the axis A is equal to I sub A times angular acceleration. So it's like everything works just the same, but now we're talking about the changing orientations of objects instead of the linear motion of objects. Okay? Any questions about any of that right now? I'm going to have to edit that out of the video. Or I'm going to get kicked off YouTube. Okay. Okay, so I've said all I'm going to say about angular kinematics. So now we just have to define these two new quantities, the moment of inertia and the moment, or the torque. So I'll start with the mass moment of inertia about axis A. Well, I have a demonstration for this too. I'll go get it in a second. So the mass moment of inertia about this axis A is always a positive quantity, just like mass is. It's large if an object is hard to rotate. And small if an object's easy to rotate. So mathematically, the way this works is something that has a high mass moment of inertia, has a lot of mass distributed along, a big distance away from that axis A. So mass is distributed far from the axis A. And a low mass moment of inertia, it can have small mass, or if you're assuming that, for a fixed amount of mass. So two things can have the same amount of mass, and one can have a high mass moment of inertia, and the other one have a low mass moment of inertia. And the way that works is the one with high mass moment of inertia has that mass spread out a long way from the axis, and the one with a small moment of inertia has that mass compressed tightly around the axis. So the mass is distributed close to the axis A. Okay, so here's a good example of that, gymnastics example. So if you're going to do a double backflip, okay, on floor, there's a few different ways you can do it, and two of them are these two. So one is like you're rotating like that. Try it. And then the other one is like that. And if this is the same guy doing both of these two things, we're not changing the mass at all between these two. But there's a big difference in the mass moment of inertia, because the axis of rotation, is, in this case, it would be the center of mass. So there's the center of mass there. Here's the center of mass here. In this case, all of the mass is pushed as tight as the person possibly can around the center of mass. And so you have a small mass moment of inertia. Here, it's spread out almost. I mean, I guess he could raise his arms above his head, but that's the only thing he could do to get that mass spread farther from the center of mass. Okay? So this one has a low mass moment of inertia. This one has a high mass moment of inertia. So this one has a high value of I sub A, and that means, no, the opposite of that. Low mass moment of inertia, and that means it's easy to rotate. And this one has high mass moment of inertia, and that means it's hard to rotate. Okay, so if you're doing a double backflip, you get a ton more points for doing it like this than you do for doing it like this, because you can rotate this really fast. And so you don't have to get, compared to this, you don't have to get that high in the air, is the biggest thing. Because you can, in whatever time it takes to come down from this high or whatever, you can do two flips or whatever. This one you have to get super high in the air to have enough time to finish two flips, because it doesn't rotate very well. Any questions about that? What if my demo is doing these 2 double backflips? It's not. Okay, so I'm going to go, and I'm going to give you 3 formulas. They all relate to the mass moments of inertia of rectangles. So for a rectangle. Yeah. Mm-hmm. Yeah. Yeah. Mm-hmm. Mm-hmm. That's a friction thing, is because what you're doing is you get, friction is the normal force times the coefficient of friction. So your tires have some coefficient of friction. And if you put sandbags in the back, you increase the normal force with the ground. And so you increase the friction force. And so you're not as likely to slip. Okay, so let's say that we have this rectangle with a length L. So this is L. And then this is W. And I'm going to give you formulas for the mass moment of inertia if the axis is here, or here, or at any of the corners. Okay, so the mass moment of inertia about A. Well, first, let's think about, you have a feel for which of these is going to be the biggest, which one's going to be the smallest. So just think about like how far most of the mass is distributed away from each one of these in turn. You can't get, so without changing the shape of this object, you can't have the mass closer to the axis than here. That's the best you can do to limit how far things are away. So the mass moment of inertia here is going to be the smallest. The easiest to rotate, like on ice or something, the easiest way to get this thing rotating is to have the axis pointing right through the center. And then the second easiest is this one. It comes down to the distance between B and A is smaller than the distance between A and C. And then the biggest, the most difficult is if your axis is at one of the corners. So the mass moment of inertia about the center is 1/12 times the mass of the rectangle times the quantity L squared plus W squared. The mass moment of inertia about that B is 1/3 times the mass times L squared plus 1/12 times the mass times width squared. And then about C, it's 1/3 times the mass times the quantity L squared plus W squared. And 1/3 is bigger than 1/12. So you can see the progression. No matter what numbers you choose here for L, W, and mass, this is going to be the smallest, biggest, and this one's going to be in the middle. Any questions about that? Okay, so the next thing we have to define, the only other thing we have to define, is the moment or torque about the axis A. Okay, so let's say that, we just have, so I'm just drawing like some random shape. That's the idea there. And let's say that this thing rotates around an axis here. So there's the axis. So we'll call that point A. And then somewhere else, there's a point P where a force is applied. Okay, so these are just arbitrary things, and you could measure the distance between A and P, and I'll call that distance D. And then at this point P, you have a force F applied there. Okay, so for now, we're going to assume that the line between A and P and the force vector are perpendicular. Okay, so that's important for now, but we'll figure out a way to get around, because so if the only way you could calculate a moment or a torque that a force applied was if this line and the force were perpendicular, there'd be a lot of cases where you couldn't calculate that, because what if the force was applied here and the force just went that way? That could happen. But for now, we wouldn't know how to do this calculation. Okay, but we'll be able to relax that later on. Oh my God, we have 25 minutes left. Okay. So if the force vector is perpendicular to the line between P and A, then the absolute value of the moment, so I'll write that as, like that. So we're not dealing with the sign yet. We'll deal with the sign separately, is equal to the magnitude of the force times that distance d. And then we can put a sign on this. So the sign comes from which way would that force make the object rotate? And then it's the same sign convention that we used for, I guess it was angular velocity and angular acceleration. Positive means counterclockwise. And negative means clockwise. Okay, so if you think about this example, if you applied a force at this point P here, and this thing rotated around an axis there, would a force in that direction, think about just like tapping this body with a hammer at that place, would that make it rotate clockwise or counterclockwise? In this case, it would rotate clockwise, so you would calculate the magnitude as the force times P, and then you make it negative because it's clockwise. Intuitively, I think the easiest way to make sense out of what a moment is to think about trying to turn like a stuck bolt. Let's say you have a bolt here, trying to turn it with a wrench. Well, two things come into play when you're trying to turn this bolt, right? One is how much force you put on the wrench, and the other one is how far from the thing you're trying to turn you apply that force. Okay, so like if for things that are really hard to turn, you need to use a really long wrench, and you would never, if you're trying really hard to turn something, you would never put your hand here and try to turn it, right? If you know you can apply like 100 newtons of force, and you apply that force here, it's not going to turn very easily. If you put your hand here and pull down, it's going to turn more easily. But the easiest is to apply that force over here, and then it's going to be really easy to move it. And so both of those two things matter. The force you apply and the distance from the axis to where you apply that force. So if you apply your 100 newtons of force here, and the idea is that that bolt is the axis A, then you're going to produce a big moment. If you apply your 100 newtons here, you're going to get a medium moment. It's going to be half as big as the one you get there. And if you apply a force of 100 newtons right over the bolt, I mean, you could apply 1,000,000 newtons right over the bolt and it's not going to turn. You know, if you apply enough force, it would just rip the bolt right off the whatever, but it would never make it turn. So what's important is that perpendicular distance between, you know, the line from the axis to where the force is applied that's perpendicular to the force. Any questions about that? I know I have the next thing in here. Okay, so that works out fine if the line between point P and the point A happens to be perpendicular to the force. But, you know, the next question is what happens if those aren't perpendicular? But what if the force vector isn't perpendicular to the line between P and A? Well, it turns out that you can, without changing the problem, so without changing anything about the problem, you can move the force anywhere along what's called its line of action. Okay, so um, if this is some random object and this is the force, okay, so the force is acting at this point P, but you can treat it like that force is acting anywhere along this line, a line that goes through that point P and is parallel to the force vector. So if the force vector isn't perpendicular to the line between P and A, just move P along that line of action until they are perpendicular. Um, any questions about that? I'll do an example. The units for moment or torque are a force times a length. You can see that just from the definition of what a torque is. You take a force and you multiply it by a distance. And so the SI units are newtons times meters. We've actually seen a unit, a quantity that was newtons times meters before. Do you remember what that was? What we used that for? What? Yeah, right. Any kind of energy. So any kind of energy has units of newtons times meters. When we, with energy though, we call a newton times a meter a joule. Even though we could call this a joule, we call this a Newton meter so that we don't get confused and think that it's energy, you know? Don't call this a joule. It's not a type of energy. Okay, let's do an example. What? It does. It's not though. So, and I was going to say, so anybody who's used like torque wrenches or something before, you see that thing, the force times the length, like you do it in foot pounds or I don't know what are it would be or inch pounds or something like that. The inch is the length, and then the pounds is the force. Okay, so let's say we have. Okay, let's say this is a football player. We can only deal with rectangles though, so he has to be a rectangular football player. Okay. Okay, so that's a football player. And let's say that mass is what, 100 kilograms. And we're going to treat it like the axis of rotation. So how do I want to do this? Well, let's say he's on the ground. And so the axis of rotation is going to be right here on the ground. Okay. And let's say that a defensive player, oh, we need to give dimensions here. So let's say this is 0.3 meters, and let's say that's 0.5 meters, and that's 2 meters. Okay. And let's say a defensive player comes in on this side. Let's see. Okay, so a defensive player comes in over here and applies a force of, what's a good football force? I have no idea. 1,000 newtons. So that's supposed to be like at the middle of the height, 1 meter off the ground. And then another player comes in and my chair just broke on the last day of class. And another player comes in and, headhunts him, or you're not allowed to do that. If any of you are football players, that's an illegal play. But so one person comes in, boom, hits like on this side, medium high. This one comes in and hits right at the top of the head. And we want to figure out what the angular acceleration of this football player is going to be. Okay? Well, the first thing we have to do is think about what all the forces are. So, free body diagram. What forces are acting on this football player? Yep, there's a weight of 100 times 9.81, so 981. And then there's a normal force. That's where his feet are in contact with the ground, so that's going to be just some upward force N acting at that axis A. And then there's 1,000 newtons here and 1,000 newtons here. Well, we have to calculate the mass moment of inertia, and then we have to calculate the moment about A produced by each one of those four forces, and then add them up, and we'll use that angular version of Newton's second law. Okay? Anybody have any questions about what we're trying to do here? Okay, so I guess first I'll calculate the mass moment of inertia. Well, that's one of those three types that we talked about. Which one is it? So there are three possibilities. The axis of rotation is in the center of the rectangle, or it's in the middle of one side and the end of the other side, or it's at the corner. Yeah, so it's going to be 1/12 times 100 times the length, so the 1/12. That's going to be the length where we're in the middle. Okay, So this is 0.5. That was not clear. But anybody have any questions about that? Help me clarify that. Okay, so when you're using that second one, you're going to be in the middle of one length and the end of one length. The one that you're in the middle of, that length goes on the 12. The one that you're on the end of goes on the 3. So then we have 1/3 times 100 times 2 squared. And that is 100 over 48, I think. So 100 over 48 for that first one, plus 400 thirds. Can someone tell me what that is, just as a decimal? What is it? 135.416. Okay. And the units there, kilogram, meter squared. Now we have to figure out the moment for each of these four forces. So what about the normal force? What's the moment produced by the normal force? Well, the way you calculate that moment is it's the force. So it's a force times the distance from the axis to where the force is applied. What's the distance from, so the axis is here, right? The force is also applied there. So what's the distance? 0. So the moment is equal to the force times 0. So there's no moment. That's like the case where you're applying the force to the wrench right above the bolt. You're never going to turn it. So that doesn't do anything to turn it. And now let's think about the weight force. Well, in this case, the distance, remember that the line from the axis to where the force is applied has to be perpendicular to the force vector. And that's not the case right now. The line from A to P is up and down, so it's parallel to this. And so we're going to have to move this weight force along its line of action. And notice that if you move it along its line of action, you can move it right to where it acts at the axis. So any force whose line of action goes through the axis doesn't produce a moment. Okay. So in that case, we have 981 times 0 again equals 0. We just moved P along its line of action till it was at A. You can't do that with every force, but whenever you can, that force doesn't produce a moment. Okay, and now the middle force, the force applied to the middle. We have a force of 1,000. But notice that if P was here, and this is A, the line between P and A isn't perpendicular to the 100. Okay, so we're going to have to move this force along its line of action This is its line of action. Okay, so if we move this force until it gets right to the middle, then you can see that this does become, so let me draw this. So now we'll say put the force there. Okay, now the line between P and A is perpendicular to the force. Anybody have any questions about that? And so now we can just take that force, multiply it by the distance, that red line. What's that distance from P to A there? 1, yep. So 1,000 times 1. And then we also have to think about the direction. If this thing can rotate around here, which way would this force make it rotate? Clockwise, so this is negative. So we have a moment produced by that middle force of negative 1,000 Newton meters. And then for the top force, we're going to do the same thing. So instead of applying the force here, we'll move the force along its line of action. There's its line of action until the force vector is perpendicular to that line between A and P. So I'll move it to here. And then the distance is the distance. So this is P. There's the distance we want. And so that moment is equal to the force of 1,000 times what's the distance in this case? 2. And then would this one make it rotate clockwise or counterclockwise? Counterclockwise, so this one's positive. We have positive 2,000 Newton meters. Finally, we can put this into the, angular Newton's second law equation. We add up all of these moments. So 0 plus 0 minus 1,000 plus 2,000 is equal to the mass moment of inertia, 135.416 times the angular acceleration. And so we get positive 1,000 divided by 135.416 is equal to alpha. Can someone divide that? .38 radians per second squared. So is that football player going to rotate clockwise or counterclockwise? Yep, this is positive. So yeah, anti-clockwise, counterclockwise. Any questions about that? I know we went through that stuff super fast, so I'll make sure that problems that you have to do pretty simple, and any problems on the test will be pretty simple. Okay, well, thanks for being in class. It's a good semester. Don't forget to come take that post-test thing if you have lab tonight.